Hey, good evening, everybody, and welcome to another session of organic chemistry. In today's session, of course, we are going to start with chapter 3, but before we do that, let us go over the quiz problem that you guys just did, and also just a quick announcement. Our homework assignment for chapter 2, do not forget that it is due on Sunday, that is September 9. Okay, and then next Wednesday we are going to have another our online session next Wednesday at 8 p.m. And for those of you who may have problem downloading the file, the webcast in Blackboard, you may come to my office on Monday or Tuesday. Bring your flash drive, and then I will upload all of the webcasts to your flash drive, so you don't need to use the internet before you play them. Okay? So just bring your flash drive, and then I will upload into your flash drive. Okay, so let us do the problem in the quiz that we just took. Okay, let us see who's going to read this. Janisha, go ahead and read this first.
Which of the following species is a Bronsted acid?
Okay, which of the following species is a Bronsted acid? Okay, what is the answer to that? Anybody?
C.
Did you say C? Yeah. Okay. I can't see my pen here. C is correct. Why C? Because it has a proton to donate, right? Okay, this would be a Bronsted acid, right? And what is the definition of a Bronsted acid? Definition of a Bronsted acid, what is it? Any species that donates a proton. Very good. A Bronsted acid is any species capable of donating a proton. So in this particular instance here, we see that only the ammonium ion has a proton to donate. So this would be the only species in this series of molecules that could act as a Bronsted acid. But I also do want to take this opportunity to expand on the concept of acid-base reactions. Okay, for the most part, the reason I give some of these quizzes is not only to elicit active participation from you guys during the class, but also to use the opportunity to expand on some of the concepts that we discussed previously. Okay, so now if we talk about acid-base reaction, this molecule here is an example of an acid because in this particular instance, this hydrogen here is the most acidic hydrogen in this molecule. And if I therefore have a base, like sodium hydroxide, reacting with the acid, you will get water, because the base here, what is happening to the base? Let me do something here. Let me draw a bond between oxygen and hydrogen. what is happening here, the base is coming in with a pair of electrons. Let us draw an arrow to show that. The base comes in with a pair of electrons, picks up the proton, and since we are going to lose the proton, that means that this bond between this oxygen and this hydrogen, the pair of electrons, will be broken, and those pairs of the pair of electrons will go to the oxygen. And that is why we say this molecule will be donating a proton. Okay, so in order to be consistent with our electron, let me put this here. This was here originally. Okay. Now, so therefore, what do we have here? We now have this molecule here has the conjugate base. So this will be your acid. This is your base. Relative to the hydroxide anion or hydroxide ion, water will be the conjugate acid here, because that is the acid that we are going to form in this reaction. And here, the acetate anion, this acetate ion here, will be your conjugate base of acetic acid. This is acetic acid here. Now, the stability of an acid depends, the strength of an acid, in other words, how strong an acid is, depends on the stability of the conjugate base. We are going to come back to that shortly. So in this particular instance here, if I ask you, without this arrow here, if I ask you, what direction do you expect this reaction to go? Do you expect this reaction to go mostly to the right or mostly to the left? Because what happens is, most acid-base reactions generally are equilibrium reactions, in which the reaction is going either way. So, if I ask you, normally we ask you this kind of question: what direction do you expect this reaction to go? For the most part, the only way you could answer that question is to know the pKa value for the acid that was the starting acid and the acid that was formed during the process of the acid-base reaction. So in this case, let us look at the pKa value for acetic acid. For the sake of this, generally 4.76, so I will simply say 5, okay? And for water, what is the pKa value for water? It's about 15.74, so let's make it 16, okay? Now the direction of an acid-base reaction, it goes from the direction of the stronger acid to the weaker acid, okay? In this case, a lower pKa value means that the acid is a stronger acid than a higher pKa value. So between acetic acid and water, which is the stronger acid? Acetic acid. So therefore, what direction do you expect this reaction to go? To the right, exactly. So this reaction therefore will go mostly to the right. Okay, there might be a little bit to the left, but most of the reaction will go mostly to the right. And that is how you predict the direction of an acid-base reaction. You use the pKa value of the acid that are involved in the process. Now supposing I ask you, go to another one. Supposing I ask you this, I give you this molecule here. The pKa value for this is about 20. Okay? And I ask you, what direction do you expect the reaction between this compound and the hydroxide ion to go? In which case you have the hydroxide anion. Okay, I will, without giving you the direction here. So we're going to form a product. Of course, water will be formed. And the conjugate base of this will be formed because we are going to lose one of these hydrogen, and then we place a negative charge on carbon. So we have this. And that will be the conjugate base. We know the pKa of water is what? 16. So therefore, what direction do you expect this reaction to go? To where? To the left. To the left. So this reaction will go mostly to the left. Okay? A little bit of it will go here. Indeed, there are certain processes in which we could use this reaction, even though only a little bit, a little bit will go to the right. Most of the reaction will go to the left. Okay, do you follow that? So the point to be made there is, you use the pKa value to predict the direction of an acid-base reaction. This is something that we are going to come back to because this is a very important concept indeed. Okay, so we go back to here. Okay, so we answered number 1. How about number 2? Let me see, column. Donnell, go ahead and read this first. Okay. Calculate the formal charges for the labeled atoms below. Okay. What would be the formula? What is the formula for formal charge, by the way? Let's get that straight. Fc is what? Equals to what? Valence electron in the natural state. Very good. Valence electron in natural state. So that would be valence electron of atom, right? Minus what? Valence electrons that actually belong to it. That is very important. Valence electron that actually belong to that atom in that molecule, right? Okay. That actually belong to atom in the molecule. So if we use that formula, what is the formal charge on carbon? A is what? 0. Okay. So for A will be 4 minus 4 equals to 0. So that is correct. How about B? B will be equals to the valence electron for nitrogen is 5 minus 4 electrons that actually belong to it. And therefore that is plus 1. Okay, about C. C, this is here. Okay, what's the formula? 6 minus 7 equals to minus 1. Very good. So therefore this is minus 1. So since it's only 1, we don't need to place the 1 there, just say negative right there. And for the nitrogen will be, okay, and that is how you have to represent that molecule. Okay, I think everybody got the idea of formal charges. So, okay, so now let us go to the next one. Okay, I know a lot of people have problems with resonance, so I've been getting all kind of inquiry about resonance all week. Believe me, resonance is very simple, even though it is important to the organic chemists. Okay, so number 3, let me see, who do I call on here? Alfreda. Yeah, go ahead, read number 3 for us.
Which of the following statements is not true about resonance structures?
Okay. If you notice I try to trick you guys using negative, which of the following statement is not true? Which of the following statement is not true? So what is the answer? C? Oh, you said D? D as in dog? C as in cat? No, keep going. You get it sooner or later. Keep going. Huh? No. Huh? D. No. Oh, I'm sorry. No, I'm sorry. No, forget it. I'm sorry. It's not true. It is C. It is C. Did you say C or D? C. Oh, okay. C. How many people got C right? How many people got C right? Just a few people got C right. Oh, I'm disappointed. So that is not correct. C. The correct answer is C because that is not correct. Okay? Because it says which of the following statement is not true. That is not true. Yes. No, all you change is electrons. You do not change the position of the atoms. In resonance, all you change is the electron, the pi electron. Okay, or the non-bonded electron. Okay, so the answer here is C. Okay? In resonance is not an equilibrium between the structures. No. Remember I told you that, for example, I say you are an hybrid of both of your parents. That is not to say that sometimes you are your parent, your mom, or sometimes you are your dad. No. It's simply saying that there is something about you that reminds somebody of both of those parents. So you are an hybrid of your parents. So resonance is an hybrid, not an equilibrium. So C is the answer here. Did everybody get that right? No, going forward. So that is the answer. Of course, we also know that in resonance, they all may have different energies. So A, B, and C are correct. Okay? Okay. A, B, and D are correct. The only one that is not correct is C. Okay, so let us do 4. Let me see, who do I call on here? And I have not talked to you yet. Ogechi, go ahead.
Write 3 additional resonance structures for the following molecules.
Write 3 additional resonance structures for the following molecule. Okay, let us try this. So how do you want to do this? How do you want to do this? Okay. Let me number these positions here. This carbon. 1, 2, 3, 4, 5, and 6. Okay, so what do you want me to do? Move the double bond? You want to move all the 3? Okay, that's fine. You want to move all the 3. So if you do that, in other words, let us. You don't have to show the arrow, by the way, but I'm going to show you the arrow just to let you see what is being moved. Okay, in other words, you want us to move these two here so that the pi electron here will now be between this carbon number 2 and carbon number 3. And when you do that, you must move this pi electron away because carbon cannot have more than 4 bonds. So therefore, you move these two here. And when you do that, then you must move this away, right? So therefore, you move these two here. Okay, I'll be right with you. So you have so where are the double bonds? Between where? 2 and 3? Sorry. Between 2 and 3, and between 4 and 5, and between 1 and 6, right? Okay. So these two are resonance structures of each other. So that is one. Some of you wrote what I gave you. That's fine also, since I asked for 3. Okay. Okay. Now, which will be another one? And don't forget, this is the symbol for resonance, this two-sided arrow. What will be the next one? Anybody? Yeah, somebody has a question there. If I did not put the arrow? Oh, as long as the resonance are correct. The reason why I am showing you the arrow, so you see, just to show you what electrons we are moving. But if you already know it, you don't have to show the arrow. As long as the structure you are giving me is correct, that is fine. Okay. So what do you want to do? Keep in mind, all we're moving with resonance is you only move the pi electron or the non-bonding electron. So you want to move which electrons here? Between 3 and 4? Okay. So if you move between 3 and 4, that is between here. And between this, you want to start with this one here. Let me take this out. In other words, you want to move between 3 and 4. So move these two here, right? Move between 3 and 4. Move the pi electron to carbon number 4, right? Okay. If you do that, we will get this. And since you are only moving between 3 and 4, everything else stays the same. This is still here. This is still here. And then you have negatively charged on carbon number 4, and the positive charge will be here. That is an acceptable resonance structure. Okay. And any other possibility, you could draw another one in which, for example, you move between 5 and 6. Right? Everything else stays the same. Okay, move between 5 and 6, right? Can you do that? You want us to do that? No, we don't need to. Anyway, so you could do that. And if I ask you, let me call this A. Between resonance structure A and resonance structure B, which is the more stable? A. Why? Because that's less charges. Keep in mind, the less charges you have in a resonance structure, the more stable that resonance is. Okay. Okay, so very good. So I think you guys got the idea of resonance, and we are going to be using resonance throughout the rest of the semester. Yes.
Could you put a flag
Onto the nitrogen. Okay. Let me ask you this. What kind of hybridization do you think the nitrogen is? It's sp3. It does not have a p orbital. Okay, it does not have a p orbital. Okay? Okay. So now let us go to start with chapter 3. Okay, for chapter 3. Okay, let us see. Tiffany, can you read for us what are we going to be doing in chapter 3?
Yes. Nomenclature, alkali groups, classes, families of organic compounds, the structural isomers, conformational isomers, and reaction of alkane.
Okay, so that means we are going to be busy with this chapter, right? This is actually the beginning of organic chemistry. Okay, so all we have been doing so far is just laying the foundation for organic chemistry, giving you some of the basic principles and concepts, and all of those principles and concepts, we are going to begin to use them going forward. So, of course, so now we're going to start the chemistry of alkanes. In so doing, we will discuss nomenclature of alkanes, discuss alkyl groups, then also introduce you to different classes of organic compounds. Sometimes we refer to them as families of organic compounds. And then we're also going to discuss constitutional isomers, conformational isomers, and before we leave this chapter, we begin to introduce you to the concept of reactions in organic chemistry. Okay, of course, as you know, before we start anything else, we're going to show you the slide that gives you the what we call the learning outcomes. These are all of the things that we expect you to learn or to master at the conclusion of this chapter. Can anybody read me a couple of these? Yes. Okay, very good. So we should be able to identify the organic functional groups. Okay. Yeah, one more. Okay, identify classes and families of organic compounds. Very good. So we should be able to do those things. Meki, can you give me two more? Okay. Okay. So the point to be made here is, thank you. The point to be made here is, as we go along in this chapter, keep coming back to this page and ask yourself, do you really know all of these items here, these topics here? Have you mastered each one of these concepts? If the answer is no, then you know that you need to really go back and do some more studying. Or sometime you may want to come and see me. Okay, so so now we're going to start with the chemistry of organic compounds. And in doing that, the first set of organic compounds we are going to encounter is what we call the alkanes. As you can see here, alkanes are organic compounds that contain only carbon and hydrogen atoms, in which all of the bonds are sigma bonds. And sometimes we refer to this class of compounds as unsaturated. Oh, I'm sorry. No, I don't mean that. Sometimes we refer to them as saturated. compounds. Saturated simply means that we do not have any pi bonds. All of the bonds are sigma bonds. And as a consequence of that, the alkanes are mostly very, very unreactive. Because all of the bonds you have in these molecules are single bonds. Keep in mind, sigma bonds are those in which you have the orbitals have head-to-head overlap. So these are very strong bonds, so they do not lend themselves to chemical reactions very easily. Okay. Examples, as you can see here, you have the methane, in which you have only one carbon atom attached to 4 carbon atoms, ethane, 2 carbon atoms, propane, butane, and as I've told you before, these are the components of your cooking gas. And you will see in the alkanes that the geometry of those carbon atoms within the alkane molecule is a tetrahedron geometry in which the bond angle between all of the bonds are 109.5 degrees, just like what you have here. The same thing here, between this and this, 109.5 degrees. We also know, because of the fact that the bonds in the alkanes are very much what we call covalent bonds, they are, for the most part, non-polar molecules. They are non-polar molecules. Now, what does that mean? What this means is the alkanes would not be soluble in polar solvent, like water, like methanol, which is an alcohol. By the way, most of your gasoline is made up of mixtures of some different types of alkanes. As you can see, if you mix your gasoline with water, what happens? What happens? Do they mix? No, they do not. Because the alkanes are non-polar, the water is polar. They do not mix. Okay, so these are some of the features of alkanes. And of course, the lower molecular weight alkanes, which is what we show you here, they are gases. Bless you. The lower molecular weight alkanes are gases, whereas those alkanes that contain more than 5 carbon atoms, from 5 carbon atoms and above, are liquids. And then those that contain over 25 carbon atoms per molecule, they are solid, like your petroleum jelly. How many people have used petroleum jelly before? Yes. So those are alkanes. So when you're rubbing your body with petroleum jelly, all you're doing is rubbing with alkane. Okay, those are high molecular weight alkanes. Okay. Okay. So anyway, so basically therefore, alkanes are those molecules that contain only carbon and hydrogen atoms in which all of the bonds are single bonds. And so sometimes we refer to them as saturated hydrocarbons. Saturated hydrocarbons. Hydrocarbon simply means compounds that contain carbon and hydrogen. Now, what we want to do first, what time do we have? Of course, we have plenty of time. You got that right, didn't you? You got plenty of time. I saw you yesterday.
Me?
Yeah, I knew where you came in my class yesterday.
Oh.
You didn't know I know that either. Okay. Okay. But we won't tell them. We won't tell them. Okay, so what do we have? The first thing we are going to do with alkanes is begin to study the nomenclature of alkanes. Nomenclature simply means naming. Okay, naming alkanes. And to name alkanes, we are going to use a system of nomenclature which is referred to as IUPAC. Nomenclature, which stands for IUPAC, stands for International Union of Pure and Applied Chemists. Okay, this is the body charged with the responsibility of providing the guidelines for the naming or nomenclature of organic compounds. So you are going to see us refer to this very often. I said give the IUPAC name. That simply means give the systematic name. Another way you look at it is systematic name. Okay, now what you see on this slide, you need to know all of these names, because these names are the basis for the nomenclature for most organic compounds. So you need to know them. Let me. No, go down to 20. Go to 20. Just go to. No, I do expect you to know all the way from carbon number 1 to carbon number 20. You need to know those. So you want me to give you the rest of them? You need to know. You need to know. So that molecule, by the way, these names are what we call the straight chain alkanes. These are the names of the straight chain alkane. And what do we mean by straight chain alkane? For example, if I add this CH3 attached to CH2, attached to CH2, attached to CH2, and CH3. I call this straight chain alkane, as opposed to, if I add this, CH2, CH, this here, I will refer to this as branch alkane. I refer to as branch. Okay, so the name that we have here, these are the name of the straight chain alkanes, and you need to know them. Okay, the first one, of course, which is the simplest one, is methane, right? And what is the next one? Next one. Next one. Okay. You see how easy that is? You see how easy that is? I didn't even tell you. You guys already know them. Okay, so don't worry. We'll get there. Don't worry. We'll get to the branch. I have to name the branch yet. Don't worry. Yes. Okay. So these are the bases. So all of these here, these constitute what we call the base names. For the nomenclature of all other alkanes, and indeed for the nomenclature of most organic compounds. Okay, so let us see, since you asked. Okay, so we go all the way. This is actually very easy to know. When it is 2 ethane, propane is 3, 4 is butane, 5 is pentane, which is 5. You know, pen is 5. X is 6, right? F is 7. Off is 8, right? Then non, 9. So these are easy. Yeah? Now you get it. Then you get to the decane, the 10, right? Then you go on. Right? Then you get to the on, meaning that you have 11. Do, try, about if you have 14. You see, I thought you got it. I thought you just said you got it. That would be tetra. Tetra-decane. What if you have 15? Pentadecane. Exactly. What if you have 16? Hexadecane. What if you have 17? Heptadecane. What if you have 18? Exactly. What if you have 18? What if... Oh, that. About 19. No, not decade. You see how easy that is. Okay. So, folks, you need to know this. Okay. Now, having known the name of the base name for most alkanes, for all alkanes. Oh, what did I do here? I'm sorry about that. This is not good. Okay. No, that will not work. Three. Okay, good. Okay. So this is where we are. Now, another thing I need to show you is that the general formula for alkanes is CnH2n plus 2. So you could use that formula to determine whether a molecule is, a formula is that of an alkane or not. And the N here equals to the number of carbon atoms in the molecule. Okay? For example, when you have the propane, 3 carbon atoms, look at the formula is C3H8. Okay, that is Cn plus CnH2n plus 2. Okay. Now, before we get to go further in the nomenclature of alkanes, there's another thing I also want to share with you. And that is what we call the alkyl groups. The alkyl groups are fragments, alkane fragments, that you obtain by removing one hydrogen atom from the alkane molecule. Alkane fragment obtained by removing one hydrogen atom from the alkane molecule. Okay? Now, for example, look at our methane. Look at methane. If we remove one hydrogen from methane, what do we get? We get a CH3, and the name for that is methyl. And how do we arrive at that name? To arrive at that name, we remove the ANE ending of methane, the corresponding alkane, and you replace with YL. You replace with YL. Okay? So look at our ethane. We remove one hydrogen from ethane. We therefore get an ethyl group. We say it's ethyl. We remove one hydrogen from the propane. We get this fragment here. We call the propyl group. And go down the line. Okay, so you remove one hydrogen from the corresponding alkane, then you get a fragment, and the name will now become alkyl. Remove the last ANE ending of the corresponding alkane, replace with YL. Okay, so now having said that, let us now do some examples. Examples of alkane nomenclature. Okay, let us start with this. Okay, from now on, I will be using a combination of condensed structure or semi-condensed structure. Forget all those stuff about Lewis and Kekulé stuff. No, do not forget them, but I will not be using them. So you need to know right away I will be using condensed or semi-condensed or sometimes skeletal, a mixture of all of those structures. Okay, so we have this here. Supposing I have this. Supposing I have that, what would be the name of this compound? Hexane, right? Hexane, right? Okay. Now, supposing, therefore, I come here, remove one of these hydrogens, and then I replace that with an alkyl group. And what is the name of that alkyl group? Okay. It's methyl, right? Now, to name this molecule here, this now is a branch alkane. To name this, you look for the longest carbon chain in the molecule. So, what I'm giving you now is the rules of nomenclature. To name this, you look for the longest carbon chain in the molecule. The longest carbon chain is what? 6. And then you then number that longest carbon chain, because that will become your base name. So therefore, you name this, you number this 1, 2, 3, 4, 5, and 6. And you notice when you number this, you give the numbers such that the carbon that has the branch or the substituent, in this case, this carbon here, will be given the lowest possible number. Keep that in mind. In other words, you have to start the numbering from here, not from here. Is that clear? Okay? So this therefore becomes, so to name this molecule, therefore, we'll say 3-methyl hexane. Oh, okay. Okay, the first thing when you want to give the name of an alkane, you look for the longest continuous carbon chain. Okay? Once you identify the longest continuous carbon chain, then you number them, give them numbers. Now you give them numbers such that whatever carbon that is attached to a branch or in this case, what we call a substituent. Let me write this here. Branch or substituent. In this case, this methyl group here, we refer to this as a substituent or a branch. So the carbon that is attached to a substituent or a branch must be given the lowest possible number when you number the longest carbon chain. Yes. Yes, go ahead.
Is it a carbon or is it an alkane? Like, does it have to be carbon? Like, it's only carbon that these will do it.
Well, don't forget, at this point, we are dealing with the alkanes. Okay, so we are dealing with alkanes, so it has to be the carbon atoms. Okay, so let us give you another example. Well, yeah, okay, let me go to another page. Supposing I have this. Supposing I have this, just a minute. Let me take one of these out. I want to make it interesting, right? Okay. What would be the name of this alkane? Which one? The third carbon? Oh. Thank you. I'm just trying to see whether you guys will catch that. Okay, so what will be the name of this alkane molecule? Let's start with, what is the longest carbon chain? 8? Okay, where do you start counting? From what end? From here? From here? From here? Okay, so let us see whether you are right. Okay, supposing we say this is 1, right? 2, 3, 4, that is 5, right? Where do we go? Okay, 6, 7, 8, 9, and 10. Okay. Okay, so where are the branches? Where are the substituents? If you do that, the substituents are in 5 and 7, right? 5 and 7. Let us keep that in mind. Okay. Yes. It has to be the longest continuous carbon chain. As long as you do not retrace yourself. Okay? You follow that? As long as you do not retrace yourself. The longest continuous carbon chain. Okay. Okay, so we say that is so. Supposing, okay, let us see here. Let me take this out. No. Oh yeah, we could name it. We come back. Okay, supposing we start numbering from here. From here, right? 1, 2, 3, 4. You follow that? 5, 6, 7, 8, 9. Sorry, 10. Okay, so the branches or substituent will be in what position? 4 and 6. 4 and 6. Okay, let me ask you this. Did you all listen to President Clinton's speech yesterday? It's a arithmetic, right? 5 plus 7 is what? 4 plus 6 is what? Which is lower? Remember, I told you the branches must be given the lowest possible numbers. Okay? The branches must be given the lowest possible numbers. So therefore, the numbering for this must have to start from this end in order to give the branches the lowest combination of numbers. You follow that? Okay? So therefore, what would be the name of this conference? Okay. 4, 6, very good. 4, 6, very good. Dice. You see, we have both of the substituents are the same. Okay. You have an ethyl group here in position number 4, and you also have an ethyl group here in position number 6. So since they are the same, we are going to use the prefix di to describe that. So that becomes 4, 6 di ethyl, and what is the base name? Decane, right. Okay, go ahead. Okay, 4, 6, because we start to number from this carbon, right? You follow that? And this branch here, this is a branch. It's in position number 4. It's an ethyl group. You follow that? And the other branch, which is also this one here, is in position number 6. And that is also an ethyl group. You follow that? This group here is the same as this group. And that is why we use the prefix di to say that we have 2 of them. Okay? Now supposing we have, let me see here, what time do we have? Oh, we've got plenty of time, yes.
How come it wasn't like tried? Because,
Where's the third one? Where's the third one? Huh? Where's the third ethyl group?
Okay.
You only have 2 ethyl groups as branches. You see? Yeah, okay. Now, supposing this is what we have. Supposing this is what we have. Okay? Supposing that is what we have. What will be the name? In this case, you have 2 different branches, right? What are the branches? No, just give me the name of the branches. Methyl and ethyl. In that case, you got to name the branches in alphabetical order. Okay, you got to name the branches in alphabetical order. Okay, so therefore it becomes, let me make it a little bit more interesting. Let's put the ethyl here. Let's put the ethyl here. Let's put the ethyl here. Okay. So the methyl is in position number 4, and the ethyl is in position number 6. Okay, so what will be the name? Okay, what is it? 6, exactly, 6. So it becomes 6 ethyl. Then use an hyphen to separate the numbers from the name. 4 methyl. Decane, exactly. Keep in mind, in this case, you got to give the the subsequent name or the branch names in alphabetical order. Okay? So now what we just, yes? No. What do you mean both names? This is the name for this one here. The other one was different. Okay. Okay, so I'm going to go back to my original lecture. Got a few things I want to share with you. Go back. Okay. Oh, I see. Wow, where was that one? No, what's it? No. Okay, I think I lost that one. Sorry about that. Okay. Okay, there's a few things I want to share with you before we leave. Okay. Okay, these are the rules that I just followed. So these are the rules of nomenclature. I thought I should let you know that. Okay, so you have 5 sets of rules. And the first set, of course, identify the longest carbon chain. And that longest carbon chain becomes the base name. And of course, the second one, if you have more than one longest carbon chain that could be used as a base name, you have to choose the one that has the most branches. Okay, in other words, if you say, oh, okay, you count from one end to another, this is 10, you count from one end to another, this is also 10, then to choose between those two, you got to use the one that has the most number of branches. Okay. And so anyway, you could read through all of this. This is in the lecture. Now, before we leave, let us just give you some examples, more examples. Look at this example here. What do we have? The longest carbon chain, we start counting from here. 1, 2, 3, 4, 5, 6. So this becomes 3-methyl-hexane. And then in the case in which you have this here, in alphabetical order of the branches, the longest carbon chain here, from here, 1, 2, 3, 4, 5, 6, and you have all of these branches, or subsequent, 3. So you start with the ethyl group. It's in the 4th position. This group here is in the 4th position. So we say 4-ethyl. Then you have in the 2 position and the 4th position, you have methyl groups. Then you say 2,4-dimethyl-hexane. The hexane is the base name. Okay? The same thing here. Okay, the base name here is heptane, which goes from here to here to here to here. So do not be tricked by the way the molecule is written. Okay, you have to follow the longest carbon chain, because the molecule could be written in such a way that the longest carbon chain may not be that obvious. Yes.
Okay, so say for instance, if you were given the name and we had to draw this out or whatever, for the 4-ethyl, it also has a methyl attached. So how would we know to draw that if we were, if you were giving us the name and we had
This one here?
No. The one on the right hand side.
This one here? Okay. No, because the base name is hexane.
Right, but that's not counted in the chain.
No, the longest carbon chain is hexane.
Right. But I'm talking about the branch on 4.
Okay. Yes.
Attached to the ethyl is another
No.
carbon.
No.
That's the whole ethyl.
Yeah, that's the ethyl. Yeah. Okay. So anyway, but the point you made is well taken, because very often we will give you the name and we will tell you to write the structure. So it goes both ways. And the last slide I will show you, of course, is another example of nomenclature. So when we come back on Tuesday, we are going to finish up with chapter 3, and there will be a quiz. There will be a quiz on chapter 3 so far on Tuesday. A very short quiz. Keep that in mind. There will be a very short quiz on chapter 3 on Tuesday. Yes, always get credit. Yes, always get credit. Just a minute. Just a minute.